All right, let's finish these problems, this last problem for chapter 20. Remember, we're not doing all the problems, and you'll see that when you do the homework. All right, so this is what I was left off with the last in the last video. This turns out to be 5 times 10 to the, what is it? 5 times 10 to the, where was I? 29th. There it is. 5 times 10 to the 29th. All right, kilograms. All right, so that's the mass of, 1/4 the mass of the sun, and then we have to figure out the radius. They give us the radius of 15,000 kilometers, right? So 15,000 kilometers, and of course I'm gonna go ahead and change that immediately. Of course, to meters. The reason, of course, because R has to be in meters. So I know that in 1 kilometer there are 10 to the 3rd meters. Right. So you just the kilometers cancel, and you just add 3 zeros to this. So the radius would be 15, and you could put 0, 0, 0, and then 3 more zeros. All right, so didn't come all. That's all didn't come out, and that would be meters. All right, so like 15 million meters. All right, so now we have to, with that 15 million meters, we have to calculate the volume. All right, so here let's get some room right here, and so the volume. Remember, this is problem number 7. Really A, problem 7A. So the volume is going to equal 4/3 times pi, right? So it's 4/3 times pi, and the radius that we just calculated was 15, and then it was 1,000 kilometers, and then 3 more zeros for meters, right? So now it's in meters, and we cube that. All right, and the answer turns out to be 1.4 times 10 to the, what is it, 22nd cubic meters. All right, so that's the volume. And remember, density, just as a reminder, density is, of course, mass divided by volume. Mass, in this case, the mass has to be in kilograms. All right, so the density, this is for part A, the density of this red giant is equal to the mass, which remember turned out to be 5 times 10 to the 29th kilograms, divided by a volume of 1.4 times 10 to the 22nd meters cubed. And so this turns out to be the density. This is the density of the red giant. Let's see, what does it turn out to be? 3.5 times 10 to the 7th, and it's in kilograms per cubic meter. It's divided by. All right, so that's part A, and then part B. All right, so let's see, what is part B is. What is part B? The red giant. So, yeah, I don't know how. It's not that interesting. But all right, here let's do that. Let's do this problem. With part B, you just really have to look up what the from chapter 16. Look up the solar core density, right? So this is part B. This is from chapter. I just looked this up in chapter 16. All right, so I mean, the solar core density, solar solar core, is approximately 1.5 times 10 to the fifth kilograms per cubic meter. All right, so that's fine. And then what we find out, of course, is this is really what they're asking, the density of the red giant, right? Which we just calculated what that value was. Turns out to be approximately 235 times the density of the core. So this core density, solar core. That's an R. Sorry, the core density. All right. And now how did I figure that out? Of course, all you have to do is just take you take the density that we just got, which was so this is what this is equal to, right? Take the density that we just got, which was what was it? 3.5 times 10 to the 7th, and you divide it by this number right here, the 1.5 times 10 to the 5th. 1.5 times 10 to the 5th. Right? And so that'll give you this roughly 235 times the core density. All right. So that's part B. And then part C, they want to know the density of the, what is it? The envelope, the envelope that is escaping from the red giant. All right. So for part C, this is part C, we're going to calculate the density of the envelope. All right. And they give us some numbers to use for that. All right. And so here we go. All right. So for part C, I don't know why so for part C, they give us the mass of the envelope. Mass of the envelope is 0.5 times the mass of the sun. So half the mass of the sun, 0.5 times the mass of the sun. So that turns out to be, because it's 2 times 10 to the 30th, it will turn out to be 1 times 10 to the 30th kilograms. And the size of it, let's see, so that's the mass. And then the radius of it, the radius they give us is half an astronomical unit. So 0.5 times, an astronomical unit, of course, is the average distance between the Earth and the Sun. So 0.5 AU. And of course, we're going to have to immediately change that from astronomical units. So 1 AU is, 1.5. That's supposed to be a 1. 1.5 times 10 to the 11th meters. 10 to the 11th meters, right? And of course the AUs cancel, and so half of 1 astronomical unit turns out to be 7.5. So that's a 5 times 10 to the 10th. 10 to the 10th meters. That's supposed to be a tenth. All right. So then, of course, we're going to use that to figure out the volume of the envelope. And so the volume turns out to be, of course, 4 times pi divided by 3, as it always is for any sphere, times the radius, which turns out to be 7.5 times 10 to the 10th meters, and we have to cube that. All right, so that turns out to be what? 1.77, roughly 1.77 times 10 to the, 10 to the 33rd meters. 10 to the 33rd cubic meters. All right, so we have the mass of the envelope, and we have the volume of the envelope. And so you're going to see, of course, the density is going to be really small, right? Because we're going to take this number, the mass divided by the volume, and we're going to get a pretty small density. All right, so what is that? All right, so this will complete the problem. The density of the envelope, that's supposed to be an E, envelope, all right, is of course the mass of the envelope divided by the volume, as it always is, or well, any density is the mass divided by the volume. Anyhow, the mass was, let's see, the mass was 1 times 10 to the 30th, and of course that's in kilograms, and divided by 1.77 roughly, times 10 to the 33rd meters cubed. And so this turns out to be roughly 5.66 times 10 to the, that's 10, times 10 to the minus 4th kilograms per cubic meter. All right, there we go. And then, of course, they want us to compare this to the density of the, what are we doing? The density of the red giant. The density of the red giant. Turns out to equal. So you just take what the density of the red giant was divided by this density that we just calculated, and you're going to get that the density of the red giant is of course much greater than the density of the envelope, and so this turns out to be roughly 6.14 times 10 to the 10th times the density of the envelope. All right, so just compare it. They want us to compare them. So, all right, so that was the problem 7C, and that is it for chapter 20.